Hello, everyone, and thank you for joining us for today's session. My name is Danny, and I'm the event planner for the New York Reactor Space. Before we start, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional, and on topic. Useful links will be shared in the chat. The session is recorded and will be available on demand 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. It'll run for approximately 1 hour with time for questions throughout. I will now turn it over to our speaker for introductions.
Hi, and welcome everyone to this episode of Mastering Event-Driven Orchestrations series. In this session today, we will delve into building reliable distributed systems using Python. We will first go over some explanations of distributed applications and durable executions required to create reliable and scalable systems, and over a practical use case using Python, our favorite language today. We'll learn how to implement and execute a distributed system using Conductor, a leading application orchestration platform. All right, let's kick off. And first talk about distributed applications. In today's development of applications, we can see a lot of coding of components that are mostly interconnected. The difficulty is that those components can be internal, can come from partners, or can be a public service. In the case, for instance, of an order processing system, we can have like the service to add an item to the cart into our internal system. We can, when the user goes to the payment, we can use a partner service. And if we need to send an SMS confirmation about the order, we can use a public service. So, and also for restocking, we can also go to another service that is in public. So all of this routing or chaining between services can be a complexity and a difficulty when we come to development. Because the problem is that we are working in a totally unsafe and unstable environment. And let's see why. First, the network is unstable and services can be at one point, at one time, unavailable for many different reasons. It can be technical, logical, or it can be just like a network issue, as we said. And because services are part of distributed transactions, because services, as we saw before, can be located everywhere. So we are really in the context of a distributed transaction. We need to work with failure as a norm and make sure that when we code our services, we know that this service or the service that it will be connected to can fail. In case of failure, we need those distributed transactions to be rolled back and in order to clean up some data, for example, if, of course, we didn't go through the completion of the execution of the transaction. Another problem in the context is that the business needs are never stable. And every day there is new change, there is new request from the business side, from the clients, to make changes. So we need, when we develop our system, to make sure that it is also adapted for changing. Because the components are interconnected, the routing between the services is mostly hard-coded and then makes our services difficult to reuse in other transactions. So most of the time we have like totally reusable services, but we have practical services that will use those reusable services for a particular use case. This is additional code that could be avoided. And last but not least is timeouts are pretty frequent and make the transactions totally lost in space when we don't know why, but the service is not responding at one point. Applications are today state machines. We can consider they are state machines. And I would like here to make a difference between application state and a business process state. What we call an application state is the state of the application code when each line is executed. The order of execution of the components that are made in your application is also part of the application state. And some system concerns like failures and retries, this is something that should be implemented today to maintain your application state. For example, calculate the order price by calling a service that will calculate the tax based on the delivery address. This is something that implies multiple services that needs to keep a state between two different services. While a business process state is really the state of the business entity here. For an order processing, we're going to have the order has been received, processed, and delivered. So one thing that is pretty important to build distributed reliable systems is to add durability. So let's see the explanation of what means durability and how application flows can be durable. So durable executions refers really to the ability of an application to continue functioning correctly and reliably, even in the presence of failures or interruptions or other adverse conditions. In the context of software development and system engineering, durable executions often involve multiple characteristics. Let's see them. Fault tolerance will means to handle and recover from faults or error without crashing or losing data. Let's say we are in the middle of a transaction. If there is a problem in the middle, how do we keep the execution while we are fixing the problem? And we'll see exactly that how to do that in our Python application on the lab part. Resilience is to adapt changes and continue to function even when parts of it fail or are stressed because of too many calls. The persistence is the data that and the state, the context that will be stored in a way that they are not lost even if there is a failure. Idempotency is to make sure that operations can not be executed by the same amount of data. Let's say it's an order processing, and the client will click on his application like 10 times on the button send or submit my order. If there is another ID, the order ID can be the idempotency key in that case. And your system, the application, should make sure that there will be only one order that will be processed, even if the user sent 10 times the same amount of the same values of the data. Consistency is a way to maintain a consistent state to ensure the data integrity and in case, of course, of failure. And the transactional support is a little bit what we talked about previously. It is to support a sequence of operation as a transaction that will be executed as a single unit, and any part of the transaction, if any part of the transaction fails, the entire transaction should be rolled back to maintain the consistency of the data. And there are multiple strategies to implement that. We are going to see that also. So consider the order processing flow, and if we have to code that in Python, this is a little bit the kind of code we're gonna get. So we have a process order function, and this will call some other services like calculate tax, generate the invoice, confirm by sending a SMS. So it's another function. We're going to wait for the fulfillment if we need to refill the stock, and then we're going to notify the user through his email, or we're going to send an error if there is an error in the value that we receive in the order. So what about if we have failures here? What about if the calculated task function fails, or the send order confirmed retried has been called too many times with the contract that we can have with our partner to send SMS. Let's say we have an amount of 100 SMS per month to send. If we go over that, how can we make sure that the program won't stop, or we'll make sure that this can be managed? In the case of calculate task, if there is an error, we need to understand why and fix it without losing the order. So this is really here what we're going to see, how to build something that is reliable, which means whatever, if there is a problem in the calculate tax function, the flow of the execution won't be totally lost. And same if we reach the rate limit for the send order confirmation SMS. So that brings to orchestration. Orchestration is something that all software developers are doing every day, but in different manners. And most of the case, the orchestration is made exactly by what we saw previously in the code, meaning by code, hard coding. So if we see that the evolution of the tech stack, it is in constant evolution for the past decades. I'm not going to go to the entire history, but from monolithic applications on mainframes to what we have today as a distributed application, this is really an evolution that we saw, that we experienced, and every layer have been added all over the time. Today, we see orchestration as a pure layer in the tech stack, and not part of the backend, not part of the front end, but something that will be in between in order to orchestrate the execution of the services, in order to give a state of your application, and in order to make sure that your entire system will be reliable. And we can see orchestrations everywhere today. Can be, as we said, in service orchestration, so in microservices, to route the microservices between themselves, or to call functions that are deployed in the cloud. But it is something that also exists since a while with process automation and BPM solutions, for instance. That will imply, in addition to orchestrate services, a human task to make sure that we can modelize the way people are working. We can see orchestrations also in DevOps to manage the delivery process, to manage also the release pipeline. We see orchestration in event orchestration to make sure that we can integrate between multiple external systems. We see orchestration in data orchestration with creating some pipelines in order to fulfill data lakes from a various number of existing data sources. We see it in security to implement some fraud detection, so to also automate the incident response when there is a problem that has been detected. And more recently, in AI, with AI orchestration, if you think about agentic RAG frameworks, for example, this is something orchestration can build by getting the content, indexing the content in vector databases, and populating the query with the context coming from the vector database to query the models. So let's see a little bit the anatomy of an orchestration. Orchestrations are composed of tasks that can be arranged in various ways to create complex workflow. So you can do, of course, simple workflows, but mostly it is implemented to do complex workflows with thousands of tasks that can be executed in series or in parallel. So tasks are really the basic building blocks of an orchestration that represent units of work, such as sending a message, processing data, or calling a service. They can be arranged in series, where each task is executed sequentially, one after the other. This is useful when tasks depend on the output of previous tasks, for instance. In a data processing workflow, you might first clean the data, then transform it, and finally load into a database. Tasks can also be arranged in parallel, where multiple tasks are executed simultaneously. This is useful when tasks are independent and can be performed concurrently. For instance, in a system monitoring workflow, you might check the status of multiple services at the same time. In addition to tasks, orchestrations can include structures of control, such as loop and conditional branching, to handle more complex workflows. A loop allows a task to set or a set of tasks to be repeated until a certain condition is met. For example, in a data collection workflow, you might want to keep collecting data until a certain amount has been gathered. Conditional branching allows the workflow to branch based on certain conditions. For instance, in an order processing workflow, you might want to handle orders differently based on their total value. If the value is above a certain threshold, the order might be sent to a user for manual review and acceptance or cancellation. Otherwise, it might be automatically approved. There are important concepts that help to ensure the reliability and efficiency of orchestrated workflows. The first one is rate limiting. That is the practice of controlling the rate at which tasks are executed. This can be useful for preventing overloading of downstream systems, managing resource usage, or controlling the pace of a workflow. For example, in a data processing workflow, you might limit the rate at which data is sent to a database to prevent overloading. Timeouts are used to specify the maximum amount of time a task is allowed to run. If a task exceeds its timeout, it is terminated. Timeouts can help prevent workflows from getting stuck due to slow or unresponsive tasks. For example, in a service call task, you might set a timeout to ensure that the workflow doesn't wait indefinitely for a response. Failure handling refers to the strategies used to handle task failures. This can include retrying the task, skipping the task, if it's not a strategic or critical one, terminating the workflow, or branching to specific workflow to manage compensations. This is a strategy you can put. The appropriate strategy depends on the nature of the task and the impact of its failure. For example, in an order payment processing task, you might choose to execute a specific workflow to cancel properly the order and alerting the user his order has been canceled. One of the key advantages of implementing application logic in workflows is the ability to introspect the path of task execution, visualize the workflow timeline, and quickly identify and troubleshoot issues. In case of task failures, for example, the task is visually identified and Conductor lets you dig into the task execution to see its input-output payloads and the execution log. This greatly simplifies troubleshooting, as you can quickly understand the cause of the failure and take an appropriate action. We'll see this in the example we're going to do. Let's talk a little bit more about Conductor. Conductor is an open source orchestration platform. It can be found on GitHub under conductor-oss/conductor. If you go, please give it a star and make it even more famous than it is right now. We have up to more than 15,000 stars as of today. So you can see the popularity is already made on Conductor, but it's never ending. The story of Conductor is actually not a new product. It's a product that has been built in the 2010s by Netflix at Netflix for internal purposes. At that time, step functions on AWS or Azure functions on Azure were not there yet. And as everything was a microservice at Netflix, and as the context was to get the most important amount of content to the most important amount of users, it was really a necessity to build such a system. A few years after using the product, Netflix decided to give it to the developer community and open source Conductor. Originally, the creators of Netflix Conductor left Netflix and reunited in 2020 to create Orchest and bring to Conductor some enterprise class values. In the coding part, we're going to see both the open source version as well as the enterprise version. Recently, in December 2023, Netflix decided to retire Netflix Conductor because of a new strategy to refocus on internal development and not supporting the open source development anymore. So Orchest gave a new home to Conductor. This is the URL that you can see on this slide, conductor-oss/conductor. And the community followed, of course, this new home. And as much as we introduced this year a Conductor Ambassador program, so we have Conductor developers, Conductor users that are using the product, whatever it is, OSS or the enterprise version, that wants to share their expertise to the rest of the community. So we created a Conductor Ambassador program for them to be able to be identified as an expert and help the rest of the community. If we look into the architecture of Conductor, we can see that at the very heart of the platform, there is a workflow execution service that is a state machine and that will evaluate all the workflow. And around that, task services that will be executed when the workflow will need some tasks to be executed. And each task is backed by a queue. So there is a queuing system to make sure it is also reliable. And around that, some integrations through API. There is a Conductor UI tool that is connected through the API to the system, and some integrations for external event system, and also a way to provide some metrics so that you can introspect everything that is done, look at if you have like millions of execution of workflows per month. This is something that is important to see the effectiveness of the entire system and quickly identified if there are like workflows that are taking too much time or too much resources. The storage system in two parts, one for the indexing part, one for the metadata. That's pretty much it for the infrastructure. So coding time. I'm gonna stop sharing for a moment and to stop the slides, and I will share again to show you the code part. Right, I'm gonna do present, and I'm gonna go to this one. All right, so you see the conductor repo on GitHub. This is where really you start. And the first thing to install conductor is to use Docker Compose in order to automate the deployment in a container. So this is what I did on my own machine. So if I look at my Docker desktop, I have the conductor server on this container. I have the Elasticsearch for all the indexing, and I have Redis for all the persistence. So that's the basic configuration. You have multiple configuration you can do from Docker Compose. You can use Redis, or you can use MySQL or Postgre. And once it's there, you have access to fully to the machine. So if I open a terminal, for instance, and I want to go to my Docker machine, which is this one for the conductor server, I am on the machine, and I can see what is there. I have app, see the app. This is where conductor is installed, and I have a config subdirectory. So I can go to config, and I have multiple configuration. But if I vi my config.properties, this is all the configuration that are possible, the various configuration that are possible according to the deployment that you choose. I'm gonna get out of this part, and I can exit. So everything is working here. What I would like to do is to show now, I'm going to take my visual editor. And from this visual editor, we're going to introspect what means creating a workflow that executes a service. So for that, I have a first task that is actually a very simple Python function called hello. You see def hello that has a parameter a task. A task is an object that is defined from the conductor SDK, and the task is getting a parameter, an input parameter that is message, and then we print the message and we return success. So now I can do any workflow that has this task, and I'm going to run this into my own system. So for that, I have another terminal window. And what I'm going to do is just to launch the Python 3 process order.python. So we're going to go into the very detail of this application in a second. And I'm going to open the conductor UI. Conductor UI on the open source is like this. And what I can do, I can see all the definitions. I have a Hello Python workflow that has only one task, and this task is named hello. As you can see, a workflow for conductor is just a JSON payload. It has input parameters, it has output parameters, It can be also some extra metadata, like the timeout policy, timeout seconds, etc., and a list of tasks. So here I have one task. This task has a name hello. It has a reference, hello ref. I can see the input parameter I have here, messages for the workflow. And my task has also input parameters, message. And this is automatically routed. The input parameter of the workflow is the value of that is put as an input parameter of the message. So when I'm going to execute this workflow, automatically the execution of my worker task here, hello, will be done. And we're going to receive in the task input data message. We're going to print it and return success. I'm going to go to the workbench and I'm going to select my Hello Python. The latest version is fine. I execute my workflow and I can introspect the execution. And I can see that the Hello Python workflow has been completed. This instance of the workflow, Hello Python workflow. And I can see that there was an input and output of the workflow, and there is task here that got completed with an output that is success and an input that has null, because yes, guess what? I forgot when I did execution to give a value of my message. So let's do it again. I'm going to go back to the workbench. I'm going to reselect my Hello Python. I'm going to say I have an input value that will be message, and that will be Hello Python developers. So let's execute this. So we have a new execution. And in this execution, the workflow input has Hello Python developers. And if I go now to the task itself, hello ref, as an input, it got Hello Python developer as well, because the routing between the workflow input and the task input has been made. And the output is still success. I can introspect my terminal to see that first I got none because I didn't put any input value. And the second one, I printed Hello Python developers, meaning that my code here has been executed. So the workflow is in the container and my task here is in my local machine. So how this is really working and connected, because I could have Conductor in the cloud and I could have still my worker here on my local machine. Well, when you start doing your Python application here, the only thing you have to do is you get a configuration from Conductor that will connect your application to a Conductor instance. And then you just say task handler and start processes is going to take all of the @workers using this declaration @worker to make a polling to that server to say, hey, if you have task for me, a task that is named hello, call me back. Or tell me, give me the data, and I will execute my code. This is exactly what happened. So there is no real magic here. The magic is just the fact that there is really a system that is totally distributed. So now now that we saw the very basic, we're gonna see how to implement something a little bit more complex. So as a Python developer, what I have to do compared to a regular Python application is first to install the Python SDK. And the Python SDK is I have probably here, no. I'm going to say oh yeah, I had it. Sorry. So to install it, I can do it in a virtual environment, and I just install conductor Python, and then I just need to import my conductor workflow, my workflow executor. So there is a couple of classes that I need to do, but this is basically what you have to jumpstart. Once your conductor instance is there, you can use the SDK to build your application and connect to the conductor instance. If I go back to the code, let's see something a little bit more complex. So here I have other workers. I have a validate order that's going to get an input data that is a full object, not just one message. I have a worker task called calculate task that is based on the order, address, state. If it is New York, the sales tax will be 4, California 8.85, Florida is 7, Texas is 8.2. I have another one generating voice that's going to take the amount, that's going to take the tax, and that's going to be actually, that's going to test if the total amount is lower than 10. We're going to fail the task generate invoice, and we're going to terminate the workflow. If it is, so it's a logical failure. If it is above $10, then we're going to continue and complete the transaction. We have a pay order, we have a send order confirmation, and we have a cancel order also that we can implement. So all of that, how it is orchestrated using Python. So what I can do is a process order workflow that will just say as an input parameter, I have the order object, and my workflow will be first validate order, then calculate tax, then generate invoice. And I'm going to say that the tax is actually the result of the output of my calculate tax tasks. Then I'm going to pay order, I'm going to send order confirmation. So this is the way my workflow is going to be. So I'm going to go back to my process order.python, and I'm going to say, I'm going to uncomment this. So now what I'm going to do is I'm going to register my workflow. Register workflow will call the process order workflow with a workflow executor. And I'm going to say, yes, register true. It means that I'm going to update every time that I'm going to run this. I'm going to save. I'm going to go back here. And instead of continuing on the open source version, we are going to also change and work on the enterprise version of Conductor. Sorry, let me go back to my README to export. So my first one, my Conductor server was on localhost because it was on my Docker image here on my local machine. But here I'm going to go to the cloud, orchestconductor.io. I'm going to copy this, and I'm going to export. And as you can see, when you go to an instance that is on the cloud, that is the enterprise version, you need to provide an authentication key, an authentication secret in order to validate your authentication to the Conductor instance. Now I can do the Python 3 process order.py. So it's going to create the worker before polling the task for each of the worker. And now I'm going to connect to my Conductor enterprise version. You can see the UI is totally different, even though this is the same kernel. But of course, you have additional features on this version. And I can see in the definition here that I have a process order workflow that has been uploaded with validate order, calculate task, generate invoice, pay order, and send order confirmation. So the code has been used in order to register the workflow on Conductor in the cloud. And now I can see and introspect the definition that has been executed by my code. The good thing here is that I'm going to execute it. And I'm going to say the order is going to be a little bit more complex. I'm going to say there is an ID. Let's say it's 1, 2, 3. There is an amount. We're going to say it's $100. And we're going to say there is an address. And into the address, we have a state that will be used to calculate the tax. So let's put Texas, for instance. All right, should have my order correctly set here as an input parameter. So I can run my workflow now. By running this workflow, I'm going to refresh. I can see that everything has been executed properly. And I can introspect, as we did before, that this is the input and the result is it has been confirmed. I can go back to the diagram and say, how did you calculate the task? So the input was with this, so it was the order, and then the output was 8.2 corresponding to Texas, according to the Python code we wrote. I can see generate invoice. We got this everything, and I can get the output is 108.2, which is actually the amount of the order plus the tax. So I can really introspect, but we say that there can be some issues, right? And this is where we find, so now, by definition, our Python code that is here is durable because it has been executed through a workflow on Conductor. So how can we make sure this is durable? Let's go here in my calculated task, tax, for example, and we're going to say I have a variable that is test that will be equals to order by tax. I'm going to save this. Of course, this will fail in the code because order is an object and tax is actually a float. Let's go back to my terminal and let's restart my process order to reapply my worker here. And I'm going to go back to the definition and I'm going to run it again. Let's run the same thing. I'm going to run my workflow. And if I refresh, I can see that there is a number 2 here that is on calculate task. So I can introspect what's happening in calculate task. Oh, there was multiple attempt. The attempt 0 failed. So I can see, yeah, it failed. And I can see why. What was the input? Input was correct. Let's see the log. Oh, okay. Test equals order by tax. There is something, yes, tax is not defined. It's even not a problem here. So, a problem of types. So what I can do is go back here to my worker. I'm going to remove this. And I'm going to just save again. And restart my app. Go back to the execution. And here you can see that we are still executing the workflow. We are now number 3 attempt that is actually scheduled. So as soon as the retry will be invoked, then this one will be executed again. Let's wait for a little while. Let me refresh. Should come in a few. Of course, when it doesn't work the first time, there is a retry like a few seconds after, then it's going to be 30 seconds after, then it's going to be 1 minute after. That should work now. So we can see that the first 2 attempts failed, the third attempt worked. And I didn't lose the state of my execution. I didn't lose the transaction if it was really a transaction here. And I was able to stop my application, fix the code of my application, go back to the execution to continue the flow without really doing anything. We said also that it can be an error that is also a logical error. So if I go back to my definition here and I can run, and I'm going to say the amount is $1. Remember that we have a task that calculates the generated invoice tax, says that if it is lower than $10, then we're going to put it as failed. So this is something as a developer using Python that you can control. So I'm going to run my workflow here, and I'm going to see that automatically something went wrong. When you have a lot of execution, you can just go to the execution and say, okay, I have some that are being completed, some terminated, and some failed. So I can say, oh, yeah, at that time, this workflow ID, this one failed. I click, okay, I can see it has been terminated. It's generated invoice. So it failed with a terminal error. I know it's a logical thing, so I can introspect the input and say, oh yeah, the amount is not correct. In building a reliable system, one other thing that is important is also, I'm going to go back to my process order flow. I'm going to go to run. It's also the fact that you can define an idempotency too. So making sure that this is not executed multiple times. So this is really something with conductor that you just have to parameter. I'm going to take here the same thing, and I'm going to say that the order ID value is my idempotency key. And I can choose my strategy. If it happens, do I want to fail? Or if it happens, do I want to return the existing? So let's say I want it to fail. I'm going to put like a good one, actually. 111. So I have this. I'm going to run my workflow. And I'm going to say, oh, yeah, I can't because there is already 1, 2, 3 already exist. So if I say return the existing, I'm going to run this. And then I go to the one that has been executed. I can see that this one was executed. I can introspect and go to the execution. Do I have here the time it has been done? Yeah, it has been done, as you can see, at 11:33. So So it was a little bit earlier today. So I'm sure now that there is no twice an order that can be executed. Of course, we are still in a kind of very simple example here. You can make it more complex. You can add switch and conditions with multiple case, and each case can have its own task. We have different task type. It can be, we saw that a task can be coded in Python, but it can be just an existing service that we can code using HTTP. Or it can be, I'm going to say HTTP as well. Or for those who want to play with AI and implement AI features in their existing application, you can also make some integrations with AI providers, AI LLM, vector databases, and we have tasks that for AI that are text complete, generate embeddings, get embeddings, store embeddings, search index, etc. We have a lot of different one that can be used here. We saw here the task can be run also not in parallel because they are in a switch, but if I am in a switch here, let me remove this one. And I'm gonna say I would like to have a fork. So a fork will help me to define and execute tasks in parallel. So more and more the flow can be relatively complex, and you can implement your logic here in this workflow. Another thing I wanted to tell you also, even though this dedicated session is for Python developers, each task can be implemented in any other languages, meaning that you can have a workflow that has tasks implemented in different languages by different teams. So you can have multiple teams working on the same workflow. It can be interesting if you're working in a large organization. That's pretty much it, what I wanted to share with you today. Again, if you want to jumpstart, you go to the Conductor OSS GitHub repo. Another way to bootstrap your trial is to go to play.orchest.io. This is where we have, and if you have a credential, which is my case, you're going to have access to a cloud version that is a playground for developers. So here you have access to all of the features of the enterprise version, and you can make also and see the differences between the OSS version. You can define your own workflow, and you can develop your workers on your own and on your local machine. This will work exactly the same way that I showed you before. We are running out of the time. I'm going to open the floor for a few questions if we have. One of the questions we usually have is really how to jumpstart. So I showed you that play.orchest.io is really the way to do it if you want to access all of those things. If you want to do it from the OSS version, you go to the GitHub Conductor OSS, GitHub OSS/Conductor repo. And from that, you also have access to the documentation. going to do orchest.io, and if I go to developers, I can have access to the docs. And on the docs, as a Python developer, I can directly go to Orchest Conductor Python SDK, where I can follow the simple steps that we have here to create our first Python application. Any more questions? All right, I'm going to say thank you to everyone. Oh, what's the difference between Airflow and Conductor? That's a very good one. They are both orchestrators, right? Both are used to orchestrate your application here. Of course, they have difference, even if they are targeting the same goal. Airflow is really open source with pretty low support. Conductor is supported by a company, meaning that you will always have someone to help you to implement. And if you look at the infrastructure, I went to the slide earlier and I showed the schema of the infrastructure, the diagram of the infrastructure. Conductor itself is distributed. And this is really important and makes a big difference between either BPM solutions or other orchestrators. It means that it really scales. People that are using Conductor, they are really executing millions of workflows per month. So if scalability is really something that you have as a first feature by using Conductor, this is very difficult to find if you have to go to Airflow. One other thing is the fact that Orchest Conductor, so the enterprise version, is really something that is plug and play. That can be installed nowhere, meaning like in the Orchest cloud, or it can be installed in your cloud. It can be deployed on your own account on Azure, for instance, without and with our full support. And this is also quite important because it reduces compared to using the open source version by yourself and implementing and maintaining and making sure everything is still up and running. This is something that can be very costly if you're using a pure OSS version like Airflow. You everything will be on your own. With Conductor, you have the support of an organization behind. Remember, Conductor has been made at Netflix, and the challenge at Netflix was very high in terms of scalability. Everyone today goes to Netflix. You can see that it's pretty efficient in terms of loading videos and having access to the entire library of videos. Thanks for the question. Yeah, the open source version is free, but you have to make sure to calculate the total cost of ownership. It's not just, oh, it's free, I'm going to use it. It's how many times you are spending to make sure that everything is maintained. We have some clients that said we actually would like to use more Orchest because using an open source version is more costly. And compared to some others also orchestrators or BPM solutions, Orchest Conductor, you pay what you consume, not per executions. That makes also a big difference on the invoice. All right, we are on time, 1 hour. So I'm going to thank you very much. Please contact me if you want to follow up on any questions, or if you want to try on your own. We also have a Slack channel that you can access, and I hope to see you there. And if not, maybe at the next episode of this series. Thank you very much and have a good day.